Welcome to this video, which is about Heisenberg's Uncertainty Principle, the non-spatiality of microscopic entities, and the strange physics of raw spaghetti, and many other things as well. A presentation by the Laboratory of Basic Self-Research, written, animated and narrated by Massimiliano Sassoli de Bianchi. In this presentation, you will have a chance to understand, in some detail, the famous Heisenberg's Uncertainty Principle, the Compton effect, which describes the interaction of an electromagnetic wave with a microscopic particle, the reasons of Bohr's Complementarity Principle, which is actually a principle of incompatibility, the reality or existence criterion elaborated by Einstein and his two younger collaborators, Podolsky and Rosen, the mysterious non-spatiality of quantum entities of a microscopic nature, often referred to as non-locality. But to understand all this, you must do your part. That is, you have to stay focused and listen carefully. Not because what I will say is technically difficult, it's all pretty simple. Conceptually speaking, however, it is also all a little subtle. Let us begin with a basic experiment. We are on the surface of a frozen lake by night. The physical system that we want to study is a wooden cube, and the instrument at our disposal to do this is a camera with flash. The experimental procedure is as follows. A colleague throws the cube on the ice so that it will slide on the surface of the lake without letting it rotate and assuming that there is no friction. At this point, we take a first picture at time t equals 0 seconds. This first picture shows us that the wooden cube was, at that moment, in the position x0. After exactly 1 second, that is, at time t equals 1 second, we take a second picture. This second picture reveals to us that the cube was, at that precise moment, 1 centimeter away compared to the previous position, that is, at the position x1 equal x0 plus 1 centimeter. This allows us to conclude that the velocity v of the cube is exactly 1 centimeter per second. To recapitulate, at time t equals 1 second, we know both the position of the cube and its velocity. In other words, we know simultaneously both values of these two physical quantities. This enables us to predict with certainty any other position that the cube will occupy in later times. For example, given that we know that the cube moves with velocity of 1 centimeter per second, we can predict with certainty that after further 4 seconds, that is at time t equals 5 seconds, it will be exactly in the position x2 equal x0 plus 5 centimeter. As is very easy to confirm by taking one last picture just at that moment. Let us consider now the famous uncertainty principle of Heisenberg. What does that principle exactly tell us? Well, simply that contrary to what we have just learned in relation to the wooden cube, that there is no way to determine simultaneously with arbitrary large precision both the position x and the velocity v of a microscopic particle, not even with the most sophisticated measuring instrument. Of course, there is no contradiction between this principle and our previous experiment, given that a wooden cube is not a microscopic body, but rather a macroscopic body, that is, a body of large dimensions. We can state Heisenberg's uncertainty principle in a bit more precise way with the aid of a very simple mathematical relation. This relation states that the smallest error ER of x, with which we can determine the position x of a microscopic particle at a given instant, multiplied by the smallest error ER of v, with which we can determine at the same instant its velocity v, must always be approximately equal to a specific constant c. To give an example, in the case of an electron, if we measure the error on the position in centimeters and the error on the velocity in centimeters per second, then the value of the constant c is approximately 1. To better understand the content of this relation, we can visualize it graphically by representing it as a curve of red color here. Only the points that lie on the curve satisfy Heisenberg's Uncertainty Principle. Let us choose among them the point which is closest to the origin. As we can see, it corresponds to the situation where we have reduced the most at the same time both the position error and the velocity error. But what if we wanted to further reduce, say of 1/10, the error on the determination of the electron's position? To do this, and since we are forced to move on the red curve, we must evidently shift the yellow dot to the right. But in doing this, while reducing the error on the position of 1/10, at the same time we increase by a factor of 10 the error on the velocity. Same thing if instead of the position we try to further reduce the error on the indetermination of the velocity. Very good, but let us now try to understand why Dr. Heisenberg invented, so to speak, his beautiful uncertainty principle. Let us first clarify what it means to see a macroscopic body. And let us consider once again the wooden cube. If we want to see it, we must necessarily light it up with a light source, such as a flashlight. When the light rays strike the cube, they are deflected toward the detecting instrument, which in the present case is your eye, or better, your eye-brain system. In other words, seeing an object means, roughly speaking, to detect the light from that object. We can observe that when the flashlight illuminates the cube, the latter is in no way disturbed by our observational process. This is a non-invasive process through which we are able to discover what already exists, regardless of our observation. In this case, we can discover not only the existence of the cube itself, but also its characteristics, like its form and color, and of course its specific location in space. As with the previous experiment, by our observation we are also able to jointly determine both the position and the velocity of the cube, without in any way disturbing it. With microscopic entities, however, this is no longer possible, and to understand why, we must investigate some of the characteristics of light. Light does not exactly behave like infinitely thin and straight rays, but like waves, and more specifically, like waves of an electromagnetic nature. Now, waves are characterizable by some specific parameters. In the case of so-called plane waves, one of these parameters is the wavelength, usually represented by the Greek letter lambda. The wavelength is nothing more than the distance between two successive peaks of a plane wave. But now let us ask, what happens when a wave of wavelength lambda encounters an obstacle of dimension d? Well, if the size of the obstacle is small compared to the wavelength, typically nothing will happen, in the sense that the wave will propagate undisturbed, as if the obstacle wouldn't exist. Let us take a very simple example. Consider the waves of the sea that pass under a large gangway. The poles on which rests the gangway are the obstacles. As we can observe from this photograph, the waves propagate toward the shore totally oblivious of the poles, in the sense that in no way the poles are able to deflect their direction of propagation. We are here in the typical situation where the obstacle is small compared to the wavelength of the wave and cannot be detected by the latter. What happens instead if the size of the obstacle is large compared to the wavelength of the wave? We can consider the example of a small island. As we can see on this drawing, which offers a top-down perspective, the wave coming from the north winds along the two sides of the island, thus changing its direction of propagation. And in this way, behind the island, a shadow zone results where the wave interferes with itself. We are here in the typical situation in which the obstacle is large compared to the wavelength of the wave, and is therefore able to modify in a detectable way its motion, its propagation. Thanks to these two examples, it should be intuitively clear now that the wavelength of the wave used to see an object poses a clear limit to the precision with which it will be possible to locate the object in space. In fact, if the wavelength is too large compared to the size of the object, then the wave will not be deflected by the same, and we will have no way of knowing about its presence. This means that the so-called resolving power of an optical instrument can never be greater than the wavelength of the radiation used. The resolution of an optical instrument, however, depends not only on the wavelength but also on the angular aperture of the instrument, because of the well-known refractive phenomena that are able to blur the image of objects, placing a limit to the details that we are able to distinguish. Now, the greater is the angular aperture alpha of an instrument, and the better will be its resolution. So, summing up, the resolving power of an optical instrument, such as a microscope, will depend both on the wavelength lambda used and on the angular aperture of the lens. It is possible to synthesize all this with the following simple mathematical expression, which states that the minimum error ER of x we commit in determining the position x of a body, because of a limited resolving power of an instrument, is directly proportional to the wavelength lambda of the radiation used and inversely proportional to the sine of the angular aperture alpha of the instrument. That said, if you have never heard of a sine function in trigonometry, do not worry, it doesn't matter a lot for the continuation of our reasoning. Now, as can be seen from this simple relation, if we want to reduce the error in the determination of the position x, a possible strategy is evidently the one of reducing the wavelength lambda of the radiation used. This, of course, is always possible, as an entire electromagnetic spectrum is available, virtually infinite, ranging from radio waves of long wavelengths up to so-called gamma rays, whose wavelengths are very small. Therefore, using a radiation of the gamma type, it should be possible, at least in principle, to detect the position of the tiniest corpuscles, such as electrons. Now, as we have seen, to see where an object is means to send on the object an electromagnetic wave and then look at the scattered wave. In other words, the wave will have to interact with the electron. But what does it mean in this specific context to interact? To fix idea, let us first consider the simple case of two marbles able to slide without friction. The first, of blue color, is immobile, while the second, of red color, impinges the first with velocity v. Let's see what happens. We can observe that following the interaction, that is, following the collision, the red marble has exchanged a certain quantity of momentum and consequently a certain amount of energy with the blue marble, which therefore has been set in motion with a certain scattering angle. For those who have forgotten, remember that the momentum of a body of mass m is simply given by the product of m times the velocity v of the body. Fine, but what happens now if the blue marble, instead of being a macroscopic body, is an elementary particle, such as an electron, which for convenience I will still represent like a marble. And the red marble is not anymore a marble, but an electromagnetic wave. Okay, let's see. I'm sure you have also noticed that the interaction process is very similar to the previous one. In fact, the incoming wave, as if it were a marble, communicates to the electron a certain quantity of momentum, also in this case by setting it in motion. But let us look more closely at what happens to the scattering wave. Let's look again to the whole process a bit in slow motion. I hope you will have noticed that the wavelength of the incident wave following the interaction has changed, in the sense that it has increased. This effect of increase of the wavelength is called Compton effect, because it was discovered by the American physicist Arthur Compton in 1922. What I want here to highlight is that electromagnetic waves, similarly to moving marbles, also possess a certain amount of momentum, and when they interact with elementary particles such as electrons, they transfer to them part of their momentum. And when this happens, their wavelengths change in the sense that it increases. This means, among other things, that waves possess a momentum which is inversely proportional to their wavelength. We have used here the color red to indicate the momentum of the wave, just to distinguish it from the momentum of the particle that we have denoted in blue. So, when waves interact with a microscopic particle, as we have seen, they transfer to it part of their momentum. But to exactly determine the value of the momentum transferred to the corpuscle, it is not sufficient to know the wavelength of the scattering wave. You also have to know the scattering angle. This is because momentum, like velocity, is a vector quantity, and vectors quantities may vary for two distinct reasons: because it varies their numerical value or because it varies their direction. Now, if you don't understand this, don't worry, it's not an essential point for understanding what follows. But what you have to keep in mind is that to determine the quantity of momentum transferred to the corpuscle, you must determine the scattering angle. But the precision with which you can determine the scattering angle is limited by the angular aperture of the lens, by the opening angle. Now, with a simple geometry reasoning that I leave to the viewer with some basic knowledge of trigonometric function, it is easy to see that it is not possible to determine the amount of momentum transferred to the microscopic particle with an error ER of P lesser than the sine of the scattering angle multiplied by the momentum possessed by the incoming wave, indicated here in red. Now, as we have seen, the momentum of a plane wave is simply given by the Planck constant h divided by the wavelength lambda. Substituting this relation in the previous one, we obtain then the following expression. At this point, if we remember that the momentum of the particle is given by the product of its mass m times its velocity v, we can divide by m on the right and left sides of the expression, thereby obtaining the minimum error ER of v on the velocity. On the other hand, we have seen earlier that the minimum error ER of x on the position of the particle is given by the ratio of lambda and sine alpha. So, multiplying these two expressions, we get this expression, which is nothing but Heisenberg Uncertainty Principle we have previously introduced. This strange situation, expressed by Uncertainty Principle of Heisenberg and many other situations that we encounter when studying microscopic systems, has been summarized by Niels Bohr in his famous principle of complementarity. Roughly speaking, this principle states that there are properties that are mutually exclusive and therefore cannot be observed simultaneously during the same experiment. Therefore, according to this principle, if we measure, that is, if we observe with good precision the position of a particle, we alter in a profound and totally unpredictable way its velocity and vice versa, as position and velocity are precisely mutually exclusive quantities. At this point, two remarks are in order. The first is that this alteration, for example the velocity when we observe a position, takes place in a completely unpredictable way, that is, not determinable a priori by the observer. This aspect of the unpredictability does not emerge directly from our simplified analysis of the Compton effect. However, it is an integral part of the formalism of quantum theory. To put it simply, according to quantum theory, we cannot determine in advance what will be, for example, the scattering angle following the collision, but only calculate the probabilities associated to the different possible scattering angles. The second remark is that in all our reasoning, we have implicitly assumed that the microscopic particle possessed, even before being observed, a specific position and velocity. This assumption, however, as we shall see, is completely unfounded. Very well. Having said that, let us return to Bohr's principle of complementarity, which expresses the fact that there are properties, such as position and velocity, which, being complementary, cannot be observed simultaneously. Now, the word complementarity is obviously quite attractive from a philosophical point of view and certainly is correct, but it could induce in a possible misinterpretation of the issue we are analyzing here. Instead of the term complementarity, we can use the simpler and more direct term of incompatibility, in the sense of the incompatibility of the procedures of observation of certain properties. In physics, one tries to make precise the concept of experimental incompatibility by using the idea of non-commutability. Let me explain. If two observations are compatible, then the order in which we perform them should not affect the final result of the observation. But when this is not the case, it means that the two observations are incompatible. This is exactly what happens with the position and the velocity of a macroscopic particle. In fact, to observe first the position and then the velocity does not produce the same result than to observe, that is, to measure first the velocity and then the position. This is mainly due to the fact that these observations are invasive, that is, they modify the state of the observed entity in an unpredictable way. However, it is important to understand that the incompatibility we are here talking about is not a feature only of the microscopic processes. It is indeed also manifest in the many operations we perform every day. Let's take a simple example. I guess everyone will agree that to put on the socks first, then the shoes, does not produce the same result as to put on the shoes first and then the socks. These two procedures are, therefore, mutually incompatible in the sense of being non-commutable. Their order of execution is crucial for the final result. But of course, not all procedures are mutually incompatible. Many are perfectly compatible. Let's take a simple example of two compatible operations. That is, of two operations whose order of execution can be switched without affecting the final result. To put on socks first, then the gloves, is the same, that is, it produces the same result than to put on the gloves first and then the socks. But let's consider some further examples of operations which are not compatible. A novice asked the prior, "Father, can I smoke when I pray?" And he was severely reprimanded. A second novice asked the prior, "Father, can I pray when I smoke?" And he was praised for his devotion. In other words, to pray and smoke does not produce the same effect as to smoke and pray. Here the non-commutability is expressed through the order chosen for the verbs to smoke and to pray in a sentence. If you switch the order of the verbs, it also changes the perceived sense of the phrase. The verbs, in fact, indicate actions, that is, operations that we perform, which is the reason why the order in a sentence is sometimes so important. What we must understand is that in general, the order with which we operate in reality affects the final result. To assemble IKEA furniture, it is necessary to operate in exactly the sequence indicated in the instruction manual, if you really want to get the desired result. To make sure that this issue is fully understood, let us consider another example. We consider the system of a simple right triangle. Then we define the operation A as the operation which consists in rotating the triangle 90 degrees clockwise. The operation B instead, by definition, is to reflect the figure of the triangle with respect to the vertical axis. Let's see what happens if we execute first A and then B. Well, now we commute the order of the operation and see what happens if we execute first B and then A. As you can see, the final result is no longer the same. A and B are operations that are incompatible in the sense of non-commutable. So now that we have clarified the concept of incompatibility and the fact that incompatibility can be expressed in terms of non-commutability, let us see what are the consequences of all this when we try to observe two specific properties of an ordinary macroscopic entity to you now familiar, a wooden cube. The system we want to study is, therefore, a simple wooden cube. With the letter A, we denote the process of observation of the property of the cube of burning well. On the other hand, with the letter B, we denote the process of observation of the property of the cube of floating. Of course, there are a number of different possible ways to define the properties of burning well and floating. So if we want to be more precise, we must specify what it means in practice for our cube to observe these two properties. That is, what are the operations we have to perform and the results we have to obtain to successfully observe these two properties. The observation of the burning well property involves exposing the cube to the flame of a match for a few seconds. If, following this operation, the cube is set on fire and reduces to ashes, then the observation of the burning well property is successful, and we can say that the property has been confirmed. The observation of the floating property consists instead in completely immersing the cube in a container filled with water, and then check if, thanks to Archimedes' buoyant force, it raises to the surface. If this happens, the observation of the floating properties is successful, and we can say that the property has been confirmed, that is, it has been observed. Considering our previous discussion, it is natural to ask now the following question. Does the wooden cube possess both properties, burnability and floatability? One way to possibly verify this consists in taking a wooden cube and try to observe these two properties, one after the other. Okay, let's see what happens. If we start with the burnability, we can see that the cube burns well, and thus turns into a small pile of ashes. But then if we try to observe its floatability, plunging the ashes in the water, these will not raise to the surface, since, as is well known, ashes do not float. The conclusion of this series of observations is that the wooden cube burns well, but does not float. Okay, so let's try reversing the order of the two observations. If we start with the floatability, we can see that the wooden cube floats easily. If, however, we subsequently try to observe its burning well property, subjecting it to the flame of a match, this will not burn, since a wet cube, as is known, does not burn well. The conclusion of this series of observations is that the wooden cube floats, but does not burn well. What we have just pointed out is the simple fact that the observational processes A and B associated with the properties of burnability and floatability, respectively, do not commute. In other words, they are mutually incompatible. Therefore, it doesn't seem possible to jointly observe the burnability and the floatability of the wooden cube. But if this is true, then one wonders, does the wooden cube really possess at once both properties of burnability and floatability? The question is legitimate, since apparently we are unable to observe altogether these two different properties, or even one after the other. On the other hand, according to our intuition, the wooden cube possesses at once both property of burning well and floating. In the same way that, for example, a car can be at the same time crash-proof and 4 meters long. Intuition tells us that an entity can possess at once a number of different properties, although not all of them are necessarily observable at the same time or one after the other. Very well, let's recap. It is clear to everyone, I hope, that the cube possesses the property of burning well. It possesses such property because if we execute test A that allows to observe it, the test will invariably be successful and the property will be confirmed. In the same way, it is clear to everyone, I hope again, that the cube possesses the property of floating. It possesses such property because if we execute test B that allows to observe it, the test will invariably be successful and the property will be confirmed. Perfect. But since our intuition also tells us that the cube possesses the meet property of burning well and floating, it is quite natural to ask, what would be the test C allowing us to confirm the meet property of burning well and floating? In other words, how can we check if it is true that the cube possesses at once these two properties, simultaneously, despite the fact that they are mutually incompatible in experimental terms? We are faced here with a little puzzle. In fact, if we take a look at the truth tables of classical logic, we can observe the following. Reading the first line of the table, we see that if a property A is false and the property B is false, then inevitably also the meet property A and B is false. In other words, the meeting of two falsities is once again a falsity. But as evidenced by the second and third lines of the table, it is also sufficient that only one of the two properties is false to make the associated meet property as a whole false. In fact, as it can be deduced from the last line of the table, the meet property A and B can be true if and only if both property A and property B are true. With regard to this, we can of course only agree. But if we consider that the burnability and floatability are mutually incompatible properties, how can we bring out their joint trueness? In other words, how can we test together, conjunctly, all at once, the truth value of two properties which are experimentally mutually incompatible? I hope it is clear to everyone what is the relevance of this discussion in relation to the previous analysis of Heisenberg's Uncertainty Principle, on which of course we will be back shortly. In fact, if you remember, the position and the velocity of a microscopic particle are linked by an uncertainty relation, a relation which in turn expresses a condition of incompatibility. Does this mean that the microscopic particle is not able to jointly possess a position and a velocity? That is, Is perhaps Heisenberg Uncertainty Principle a statement about the simultaneous non-existence of position and velocity of a microscopic entity, such as an electron? Or is it just a statement about our limitation in jointly knowing these physical quantities? Based on our intuition about the burnability and floatability of a wooden cube, we would be tempted to say that the experimental incompatibility of two physical quantities does not mean that this quantity cannot exist simultaneously, and that therefore nothing prohibits an electron to simultaneously have a position and a velocity. But is this true? To find out, we must continue our conceptual analysis. And let us begin by defining a bit more clearly what a property is. In general, we can say that a property is something that an entity is able to possess regardless of its context. Properties are observed and defined by means of experimental tests that, if executed, enable one to confirm or to invalidate the property in question. But be careful. To confirm a property does not necessarily mean to prove that the property is actual in the sense that it was or is stably possessed by the entity in question. A burnt wooden cube is no longer a burnable wooden cube. That said, to continue our exploration, we now need the help of Einstein and of his two capable collaborators, Boris Podolsky and Nathan Rosen. In a famous article published in 1935, these three scientists enunciated an important realities criterion, which is also an existent criterion, since in the common understanding of these two concepts, something is considered to be real if and only if it exists. More precisely, Einstein, Podolsky and Rosen, in their famous article, enunciated the following realities criterion. If, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. What Einstein, Podolsky and Rosen have clearly recognized is that our description of reality is essentially based on our dependable predictions about it. However, they remain rather cautious regarding their criterion, as they also wrote in their article that it seems to us that this criterion, while far from exhausting all possible ways of recognizing a physical reality, at least provides us with one such way, whenever the conditions set down in it occur. Regarded not as a necessary, but merely as a sufficient condition for reality, this criterion is in agreement with classical as well as quantum mechanical ideas of reality. But despite their warning, Einstein, Podolsky and Rosen didn't offer a single counterexample of what would be the nature of an element of physical reality not subject to their criterion. In other terms, although they assume very prudently that their criterion is only sufficient, they presented no reason as to why it shouldn't be considered also necessary. But let us come back once more to the wording of the criterion. An important point to emphasize is that when the three scientists say, or better write, if we can predict with certainty, what one should understand is if we can in principle predict with certainty. In fact, the crucial point is not if we do possess in practice all the relevant information allowing us to make a reliable prediction, but if this information is available somewhere in the universe, although maybe dispersed who know where, so that a being of sufficient power and intelligence could in principle access it. That said, it is worth observing that this important criterion of reality or of existence was subsequently reconsidered by the Belgian physicists Constantin Piron and Diederik Hertz, the latter being also the author of the example of the floatability and burnability of a wooden cube. So these two physicists reformulated the criterion in a much more specific and complete form, which is roughly the following. If, without in any way disturbing the physical entity under consideration, it is at least in principle possible to predict with certainty the successful outcome of an observational test, then the property associated with that test is an actual existing property of the physical entity. And vice versa. That is, if the property of the physical entity is actual, then, without in any way disturbing it, it is in principle possible to predict with certainty the successful outcome of an observational test associated with it. Therefore, according to this reality criterion, which for simplicity we will simply call Einstein's criterion, a property is actual if and only if, should one decide to perform one of the observational tests that defines it, the expected result would be certain in advance. This means that the entity has the property in question before the test is done, and in fact even before one has chosen to do it. And this is the reason why one is allowed to say that the property is an element of reality, existing independently from our observation. On the other hand, if we cannot apply the criterion, that is, if we cannot, not even in principle, predict the outcome of an observational test defining the property in question, then we must conclude that the entity under consideration does not possess that property. That is, that the property is not an actual existing one, but just a potential property. This conclusion is correct provided, of course, that the prediction cannot be made even in principle. In fact, in most experimental situations, we simply do not possess a complete knowledge of the entity, and therefore we haven't access to all its actual properties. But when we do possess a complete knowledge of the entity, then by definition we are able to predict with certainty all that is predictable about it, and therefore what cannot be predicted is by definition a non-existing, potential, uncreated aspect of reality. Well, I hope not to have confused the issue too much with this important and profound criterion of reality. But let us return to our wooden cube. So, based on the reality criterion of Einstein, revisited by Piron and Hertz, to determine whether the wooden cube possesses or not the property of burning well, we don't have to execute the burnability test and burn it, but simply to be in a position to predict with certainty that, should we perform the test, the outcome would be certainly positive. Consider a much more straightforward example. Just think about Venice now and ask yourself, does Venice exist right now? I'm assuming, of course, that in this moment you are not in Venice. Now, according to the reality's criterion, to be able to say that Venice exists in this moment, you don't necessarily need to have an experience with Venice in this moment, but simply be able to predict that if you would have decided to have such experience, Venice with certainty would have been available to it. So, summing up, reality, what exists, doesn't correspond exclusively to the phenomena that we factually experience. Reality also and mainly correspond to the possible phenomena, those that we could have experienced with certainty if only we would have chosen so. Reality, therefore, is constructed in a counterfactual way, in the sense that we can speak in a meaningful way even of things which, in fact, we are not concretely observing, provided that if we would decide to do so, the result would be absolutely certain. Now, how can we apply all this to the problem of our wooden cube? More particularly, how can we solve the problem of being able to demonstrate that the wooden cube actually possesses the meat property of burning well and floating, although these two properties are experimentally mutually incompatible? According to Einstein's criterion, it is sufficient to be able to predict that should we perform the test C associated with it, the positive outcome would be certain. Alright, but what would be this test C associated with the meet property of burning well and floating? In other words, what is the observational test of a meet property A and B? Well, you should know that the specification of this particular test, which in technical language is called product test, were discovered some years ago by the physicist Constantin-Piron, which I already mentioned in relation to the Einstein-Podolski-Rosen criterions of reality. Let's see exactly what a product test is. It is very simple. First of all, we need an instrument that can generate in a completely random way two events, which we will simply call heads and tails. For example, this instrument could be the toss of a coin, provided that the toss is carried out in such a way as not to allow the experimenter to predict the outcome in any way. So, if following the toss of the coin we obtain heads, say, we perform test A, and the outcome, positive or negative, is assigned to the test C of a meet property. On the other hand, if we obtain tails, we perform test B, and again, the outcome, positive or negative, is attributed to C. That's it. Now you know the specific nature of the observational test of a meet property, called, in technical language, a product test. Perhaps you will object that since after the coin toss we have to perform only one of the two tests, this means that only one of the two properties would in fact be tested or observed. But this is not exact. You don't have to forget that the toss of the coin is an integral part of the observational procedure, so that the choice of which of the two tests is performed is totally unpredictable. Therefore, the only way to ensure a priori with certainty the positive outcome of test C without the need to execute it is that the cube possesses both properties at once, that is, that it possesses them at the same time. So when we go from the properties to the test, the logical operator AND, the operator of conjunction, transform into the logical operator OR, the disjunction. To test the meet property C, which is A and B, we have to test A or B, choosing, however, one of these two alternatives, and this is a crucial point, of course, at random. That said, what can we say then about the meet property of the cube of jointly burning well and floating? Does the cube possess it in actual terms or not? Evidently, according to the test product C just defined, and according to Einstein reality criterion, being able to predict with certainty the positive outcome of both tests, of burnability and floatability, we can deduce that the wooden cube jointly possesses these two properties at once, although they are mutually experimentally incompatible. In summary, the experimental incompatibility of two properties A and B doesn't necessarily mean that they cannot be simultaneously actual for a same entity, as the example the wooden cube clearly demonstrates. As a result, we may be tempted to conclude that even though the position and velocity of a microscopic corpuscle are incompatible physical quantities, as evidenced by Heisenberg Uncertainty Principle, nevertheless we can consider them simultaneously actual. Right? No. Wrong. Let us try to understand why the position and the velocity of a microscopic particle, contrary to the burnability and floatability of a wooden cube, cannot be property, however incompatible, possessed at once by the microscopic entity. Let us consider again the case of a macroscopic body, that is, of a body of large dimensions. At time t0, The body is located in a given position x0. And at that same instant, it also possesses a determined velocity v0. As we previously discussed, we know that when we concurrently know the position x0 and the velocity v0 of a body at a given instance t0, we can calculate, thus predict with certainty, any other position that the body will occupy in any subsequent instant by solving the so-called equations of motion. We can, for instance, determine its position x1 and velocity v1 at a subsequent instant t1, or its position x2 and velocity v2 at a further instance t2, and so on. This means that the body goes along a trajectory in space as time passes by, which is perfectly defined, that is, a priori knowable with certainty. Therefore, to solve the equation of motion is equivalent to predict with certainty any future position and velocity of the macroscopic physical body in question. We will not enter here into the details of these equations of motion, which, depending on the physical system, can also become quite complex. What is important to understand is that the equations of motion are a sort of mechanical device, and that when we feed this device with a precise input, formed by a position and a velocity evaluated at the same instant of time, say at time 0, then the device will invariably yield outputs corresponding to the position and velocities at any other instance of time t, both in the future and in the past. It is on the basis of this remarkable property of the equation of motion that the Frenchman Pierre-Simon de Laplace, towards the end of the 18th century, enunciated his famous principle of determinism, more or less in these words: if at a certain moment we would simultaneously know the position and the velocity of all bodies of the universe, then, in principle, we could predict their behavior at any other time, both in the past and in the future. For Laplace, the simultaneous knowledge of the position and velocity of all bodies in the universe was entirely possible, at least in principle. However, due to Heisenberg principle, we today know that he was wrong, that a knowledge of this kind is absolutely unthinkable, and this not for a lack of information or of inadequate technology. Indeed, there is no way to simultaneously determine the position and the velocity of even a single electron, let alone all those in the universe. Indeed, if you remember, Heisenberg Uncertainty Principle doesn't allow us to jointly determine with arbitrary precision the position and velocity of a microscopic entity. So, we have no way to insert in the equation of motion the input required, and consequently the equation of motion are no longer able to provide the desired output. And accordingly, we are no longer able to predict in no way the position and velocity of the microscopic entity at any other instant of time. And this means that the principle of determinism, as it was enunciated by Laplace, is not valid for a microscopic entity. But failing the ability to determine, that is to predict with certainty, the future position and velocity of the microscopic entities, what can we conclude on the basis of the realities criterion of Einstein-Podolski-Rosen? Well, it is very simple. The criterion tells us that the possibility to predict with certainty the position and or velocity of the corpuscle is equivalent to the reality, that is, to the existence of this same position and or velocity of the corpuscle. But if the possibility of predicting this quantity fails, in the sense that they cannot be predicted even in principle, then it means that they cannot be considered as real, as existing quantities. So we are forced to conclude that microscopic particles, electrons, protons, neutrons, atoms, molecules, etc., simply do not exist. in the sense that they do not exist as particles, that is, as entities localized in space with a specific position, velocity, and energy, etc. If I also say energy, it is because, as is known, the energy of a material body is in general a function of both its velocity and position. And if these two quantities are not actually existing, then the same must be true also for the energy. In short, the microscopic particles, which particles therefore are not, are non-spatial entities. If a macroscopic body is able to possess in every moment a well-defined position and velocity, a pseudo-microscopic corpuscle, instead, cannot possess in general such attributes. To say it with the thought-provoking words of the Belgian physicist Diederik Hertz, we must surrender to the evidence that reality is not contained within space. Space is a momentaneous crystallization of a theater for reality where the motion and interaction of the microscopic material and energetic entities take place. But other entities, like quantum entities for example, take place outside space or, and this would be another way of saying the same thing, within a space that is not the three-dimensional Euclidean space. In other words, the three-dimensional space in which we live with our physical body, macroscopic in nature, is only a small theater, and this little theater do not contain all of reality. Reality is much bigger than that. It cannot be represented on the small three-dimensional stage. There are other venues out there that can accommodate entities genuinely non-spatial in nature, such as electrons. Entities whose spatiality is of a very different kind, decidedly non-ordinary. But if the microscopic entity generally do not have a position, then what exactly does this mean? How can we understand such a process through which a physicist, under certain experimental conditions, detect the spatial position of an elementary entity? The answer is simple. Quantum entities are not permanently present in space. When a quantum entity is detected in such a non-spatial state, it is dragged or sucked up into space by the detection system. The spatial position, that is the location of a microscopic entity, does not exist in general before the observational process, but is created by the very process of observation, the physical process of observation. But that's not all. To tell the truth, the spatial position of a microscopic entity does not even exist after the observational process in general. Indeed, it is a property of an ephemeral nature. But how can we understand the ephemerality and incompatibility of these quantum properties? Can we find analogies that allow us to understand? Well, for this, it is sufficient to love spaghetti. By this, I mean to say that some of the mystery that we have so far explored can be clarified by studying the strange physics of spaghetti. More precisely, we will be concerned with the so-called left-handedness of spaghetti. Let's see what it is. The physical system we want to study is therefore an uncooked spaghetti, preferably a good brand. The measuring instrument we are going to use in order to perform the observational experiment, that is to perform the measurement, is the two hands of the scientist. The property that we want to observe, as we said, is the left-handedness. Yes, I know, you have never heard of the left-handedness of a spaghetti, but now I will explain what it is, by explaining you how to measure it, that is, how to observe it. You have to grab the spaghetti with the two hands, then bend it until it breaks, and if the longest fragment remains in the left hand, then the left-handedness property is confirmed, otherwise not. And if the spaghetti is already broken, you simply have to execute the test using the longest fragment. Okay, but let us try in practice. As you can observe, the test was successful. Thus, the left-handedness of the spaghetti has been confirmed. Let us now do the test once again with another spaghetti identical to the previous one. This time the test wasn't successful and the left-handedness of the spaghetti has not been confirmed. Instead, what has been confirmed is the inverse property of left-handedness, which is the property of right-handedness. Fine, but let us now consider another property of the spaghetti, simply called the solidity. So, the physical system, once more, is an uncooked spaghetti. The measuring instrument is this time formed by a single hand of the scientist and the floor of the kitchen. The property that we want to observe, as we said, is the solidity. And to know exactly what it is, we only have to describe the experimental observational protocol, which is as follows. You take the spaghetti in your hand and let it fall from your hand to the floor. If it doesn't break, the solidity property is confirmed, otherwise not. And if the spaghetti is already broken, as we did before, you simply do the experiment using the longest fragment. Okay, so let's try. As we can see, the test was successful. Thus, the solidity of the spaghetti has been confirmed. But let us do the test once more with another spaghetti identical to the previous one. This time the test wasn't successful and the solidity of the spaghetti has not been confirmed. Instead, what has been confirmed is the inverse property of solidity, which is the property of fragility. Alright, now, if you had thought carefully, you have surely realized that left-handedness and solidity are ephemeral properties. Indeed, consider the case of the left-handedness. Suppose that you have just made the observation and that the test was successful. At that precise moment, when you are still holding the two pieces of spaghetti in your hands, you can certainly say that the spaghetti actually possesses the left-handedness property. But as soon as you let go of the two fragments, that same left-handedness goes back to being a property which is only potential. In fact, once the relation between the fragments of the spaghetti and the hands of the experimenter is lost, it is no longer possible to affirm that the spaghetti is left-handed. This is because to observe again the left-handedness, you have to repeat the test using the longer fragment. But nothing a priori guarantees you that the outcome of the test will be successful again. Here, you can appreciate a fundamental difference between the observation of a property such as the burnability of a wooden cube and the left-handedness of the spaghetti. For the burnability, we were perfectly able to predict the outcome of the test without the need to perform it. On the other hand, for the left-handedness, we no longer have this option. Of course, one could argue that to make a reliable prediction, one needs to have all the necessary information. That is, to study carefully, maybe under a microscope, all the characteristics of the spaghetti in question. Perhaps also asking precise information from the manufacturer about the method of manufacture. But will this really help to predict in advance the outcome of the test of the left-handedness? If you attentively consider the way in which the left-handedness property is tested, it is easy to convince oneself that even with a complete knowledge of the spaghetti, up to the level of its molecular structure, one will never be able to predict with certainty the outcome of the observational test. This is not because we lack some essential information about the spaghetti as such, that is, about its state, but because we are totally clueless about how exactly the process of the observation of a property will take place. The outcome of the test will in fact depend on a number of variables which are somehow hidden to us and totally outside of our control, such as the subtle vibration of our hands while we act on the spaghetti, its specific orientation, the variable pressure exerted by our fingers, the rapidity with which we bend it in order to break it, and so forth. And it is the combination of all these variables and those associated with the state of the spaghetti which will determine in an extremely complex way in which points the spaghetti is going to break, thus producing the final outcome of the test. In other words, despite having a complete knowledge of the state of the spaghetti, we have no way to predict the effects of the innumerable fluctuation in the interaction between the spaghetti and the instrument of observation made by our two hands. Fluctuation that ultimately will determine the exact breaking points of the spaghetti and therefore its left-handedness or right-handedness. The logical conclusion of all this is that the property of the spaghetti of being left-handed or right-handed cannot be predicted with certainty, also when we possess a complete knowledge of the state of the spaghetti. And according to the criterion of reality of Einstein, this means that this property cannot be considered elements of reality. That is, they do not exist. Or rather, their existence is only potential, in the sense that although they do not exist in a given moment, they may nevertheless exist at a later instant. And in fact, this is exactly what happens during the process of observation. The property of left-handedness is not discovered during the observational test, but literally created during it and by it. Before the test, it wasn't existing, but by means of the test, it will possibly be brought into existence, although in a very ephemeral way. And the same obviously applies to the property of solidity. So, to summarize, left-handedness and solidity are ephemeral properties in the sense that they are potential properties that are possibly created during an observation, by the observation itself, in a way which cannot be predicted in advance, and also in a way that the property will cease to be actual at the precise moment when the specific relation between the measuring instrument and the physical entity is severed. Left-handedness and solidity are not just ephemeral property, they are also property which are mutually incompatible. In fact, the observation of the left-handedness considerably increases the probability that a subsequent test of solidity will provide a successful outcome, as is clear from the fact that the shorter the spaghetti fragment, the less easily it will break when falling to the floor. So, in general, if you perform first the test of left-handedness, then the test of solidity, for example, on a large number of different spaghetti, the statistics of outcomes will differ significantly from the one obtained by first performing the solidity test and then the left-handedness one. The pragmatic example of the spaghetti reveals us that incompatibility and ephemerality are independent concepts. Indeed, as the piece of wood example shows, two properties can stably exist although being incompatible. But also, as the spaghetti example shows, they can as well only ephemerically exist and nevertheless still being incompatible. This indicates that the ephemeral character of a property has more to do with the way the property itself is defined and tested as to the fact that it may or not entertain incompatibility relations with other properties. This remark is relevant particularly in view of the fact that in our reasoning to deduce the non-spatiality of microscopic entities, we have, if you remember, used Heisenberg Uncertainty Principle as a main ingredient. That is, the existence of a relation of incompatibility between position and velocity. Therefore, one could be tempted to conclude that it is the very existence of such an experimental incompatibility, which would be at the origin of the observed non-spatiality of microscopic entities. However, considering the piece of wood example, we see that incompatibility is not a sufficient condition for creating non-spatiality. And considering the spaghetti example, we also see that incompatibility is neither a necessary condition for it, as is clear from the fact that the ephemeral character of the left-handedness or solidity properties is really built in the very definition of them, independently of the compatible or incompatible nature of their relation with other properties. That said, I hope I have not lost you in these conceptual subtleties. What is important to highlight here is that left-handedness and solidity of a spaghetti, like the position and velocity of a microscopic entity, are non-ordinary property, that is, non-classical properties. But perhaps you are now wondering, what exactly are classical properties? Well, simply, classical properties are properties which obey the so-called classical prejudice. According to this classical prejudice, the outcome of an observational test is always a priori certain. But the classical prejudice has a limited validity and is based on the assumption that the interaction between the instrument of observation and the observed system always takes place in a predeterminable way. Now, the observational test of burnability and floatability of the wooden cube are certainly in accordance with the classical prejudice. But, as we have seen, the observational test of left-handedness and solidity of the raw spaghetti invalidate the classical prejudice. In the same way as this prejudice is invalidated by the observation of the position and velocity of a microscopic entity. Very well. Let us now summarize the most important points of our investigation. We have seen that Heisenberg's Uncertainty Principle expresses the experimental incompatibility of certain fundamental properties associated with the microscopic entities, like position and velocity. But we have also highlighted that experimental incompatibility is a widespread phenomenon, also present in the ambit of macroscopic bodies, and not only in relation to microscopic ones. Moreover, and contrary to what one might believe, we have shown that it is perfectly possible to test together also incompatible properties by means of so-called product tests discovered by Piron. We have then highlighted the content of Einstein's reality criterion, which affirms that existence and predictability are related concepts. Next, using Heisenberg Uncertainty Principle and Einstein's criterion in combination, we were able to deduce the non-spatiality of microscopic entities on the basis of the fact that to have a position is an ephemeral property of a microscopic entity, not stably possessed by it. We have seen, however, that ephemerality can also manifest in macroscopic bodies, and incompatibility and ephemerality are mutually independent concepts. Finally, we realize that wooden cubes and uncooked spaghetti can be of great help in understanding the mysteries of physics in general and of quantum physics in particular. Of course, there would still be much to say in order to elucidate these conceptually profound and subtle issues, which are of course also in part controversial. In particular, much should be added concerning the puzzling non-spatiality of quantum entities, often indicated by physicists with the term of non-locality, although the term of non-spatiality is in a sense more appropriate. I would like now to conclude this presentation with a metaphor, which was proposed in 1990 by Diederik Ertz as an attempt to invent a world of entities where the condition of spatiality of the entities that populate this world emerges from a different underlying reality, whose spatiality is of a different kind. This world of entity is, as we shall see, a world that lives within a space of friendship. Let's see what it is. The entities considered are the human beings in the future. The world of entities is the terrestrial human society. The interaction between the entity is the one, as I said, of friendship. The hypothesis here is that the human society succeeded to survive by being able to totally eliminate enmity, that is, negative friendship, and by making friendship always reciprocal. What does all this mean? It's simple. If we denote by AD of xy the function that determines the affective distance that person x feels for person y, and if AD of yx is the affective distance that person y feels for person x, then the reciprocity simply means that these two distances are identical, or to say it in more technical terms, that the AD function is a symmetrical function. The absence of enmity, on the other hand, means that the AD function is always positive, as it should be the case for a distance worth of a name. Very well, let us consider now the ordinary physical space in which we humans usually live. In this space there are people, for example a boy we will call X, and a girl we will label Y. Between these two guys there is a physical distance, PD of xy, which is the distance usually considered between the ordinary physical spatial objects. Let us now consider the friendship space. The boy X and the girl Y obviously do not exist only in the ordinary physical space, but also in the space of friendship. And in this other space, X and Y are not separated by a physical distance, but by an affective distance, which, for example, can be much smaller than the physical one. In fact, as is well known, the mutual friendship between two people doesn't depend on how distant they are in physical terms. Consider now a third individual, Z, whose physical distance with Y is, for example, small. But this time, and contrary to the previous example, their distance in the friendship space is large. In other words, we can see that the distances in the physical space and in the friendship space follow different logics. Nearby objects in the physical space can be pretty much far away in the friendship space, and vice versa. Alright, consider now the fact that in the human society, as time passes by, different subgroups of people will emerge bound by specific affinities, in the present case affinities of an affective kind. This emergence will produce, as time goes on, a structuring of a friendship interaction. Let us observe this phenomenon from the double perspective of the physical space and friendship space. As we can see, over time people will be arranged within the friendship space into macrostructures. For simplicity, we have only evidenced two of them, A and B, which are located at a certain distance from each other, AD of AB. In the old physical space of the surface of the Earth, people live mixed. But in the new structural space of friendship, they are all organized within macrostructures. To fix ideas, we can think of families, associations, interest groups, sects, etc. So as time goes on, the friendship space will, little by little, become a space of macro friendship. Now consider an individual Z. And suppose that this individual, Although at a given time he is present in the ordinary physical space, he has not yet established a specific relationship with one of the macrostructures present in the space of macro-friendship. Suppose that after a very long time, humans of the future have totally forgotten not only about the original Euclidean space associated to the surface of planet Earth, but also about the first version of the friendship space, when it was not yet structured into well-defined affective macrostructures. In this case, of course, in this structured space of macro-friendship, a single, affectively isolated individual cannot have a localization, that is, a specific position, as having a localization in the space of macro-friendship means to belong to a specific structure of affinity, in this case, A or B. Then, Z, from the point of view of the space of macro-friendship, is typically a non-spatial entity, not actually present in that space. Suppose, however, that as a result of an interaction with this macrostructure, it comes the time when, for reasons that we do not need to specify, Z decided, or is forced, to choose to belong to one of these two structures, A or B. Before that this happened, we can say that Z is in a superposition state with respect to these two possibilities. But at the exact moment that he chooses to which macrostructure he belongs, Z suddenly acquires a specific location in the macro-friendship space, becoming an integral part of one of these macrostructures, for example, the macrostructure B. It is interesting to note that this process, during which a specific localization for the elementary entity Z is suddenly created in the macro-friendship space through its interaction with the macrostructures A and B, is typically a process of creation, which is reminiscent of the creation of a position for an electron when it interacts with the measuring instrument, which are precisely structures of a macroscopic kind formed by a huge number of elementary microscopic entities organized together. Of course, this is only a metaphor, and it is perhaps time to end this already long video presentation. If you enjoyed the content of this video and would like to deepen your understanding of these topics, you may be interested in the following booklet. You can also find extra information at the following web addresses, from which you can freely download a number of interesting papers. Thanks for listening, and if you enjoyed this video, please do not hesitate to share it.